Hello there! Bonus lesson 3. This time we're going to look at molecules and the names that go along with the simple molecules that we're going to see here in grade 11. So hopefully you remember that molecules have these covalent bonds that hold all the atoms together. You might have even used some of these model kits that represent the bonds with little plastic connectors. Sometimes they have these orbital shapes that go along with them, or they're just little pegs that hold the atoms together. But that's the heart of all of our molecules, is that you're going to have all of these covalent bonds that hold together a single unit, and that single unit is your molecule. So let's look at a couple of them and how to represent them, and then we'll do the naming. So starting at the beginning, a covalent bond is the sharing of electrons between two atoms. And if the atoms have a similar electronegativity, the atoms are shared pretty much equally, and you can have slightly unequal sharing that gives you more polar bonds. And then if it's two polar, then you're over into an ionic bond. So usually for molecules, it's going to mostly be nonmetals. And for the simplest of these and the purest of covalent bonds will be when you bond two of the same nonmetal together. And so that means the electrons are going to be shared perfectly equally between them, and you're going to end up with these pairs that we represent or remember with the Hofbrinkel mnemonic to help us to keep those straight. So each one of these comes in pairs, and they all have shared pairs of electrons that hold them together. The only ones that have multiple bonds are the nitrogen and the oxygen. And all the rest just have a single bond holding them together. All of your halogens and the hydrogen. So there you go. There's your simplest of covalently bonded molecules. These are all pure covalent bonds because the two atoms have exactly the same electronegativity. So the electronegativity difference is what helps you decide what type of covalent bonds you might have. All of those Hofbrinkel molecules have no difference in electronegativity, so they're completely nonpolar. Right up to 0.4 difference here, which would be like your hydrocarbons, where there's a small difference but not enough. You'd still consider that to be nonpolar. And then beyond that, you'd get your polar covalent bonds, things like water, which are up here like around 1.4. And so with a water molecule, the side of the water molecule that has the greater electronegativity, which is the oxygen in this case, will get a negative charge, and the other side with the hydrogens gets a positive charge. So you can represent that with these little lowercase delta symbols. Plus or minus means a partial charge, or you can use an arrow and to show the two charges. And since there's two charges, it's called a dipole, kind of like north and south pole, right? And so the arrow always points toward the negative side, and you can cross this end to make it look like a plus sign so that you remember that's the positive side. Anything beyond 1.7, we call that ionic. Since we already did those, this lesson's gonna focus on the molecules below 1.7 difference. Alrighty, so let's see if we can work out using electronegativity what type of bonds we have here. First one is HCl. H has a electronegativity of 2.2, and chlorine's over here at 3.16. And so if you subtract those two, you get 0.96. And so that's going to be a polar covalent bond. And then we got carbon over here, which is 2.55. So 2.55. And this is 2.20. And so the difference there is going to be 0.35. And this is going to be a non-polar covalent bond. The other part of working out whether whole molecule is going to be polar will be the shape. And so you can refer to our Vsepper lessons in order to determine what shape a molecule will have and to figure out from both of these whether or not you'd have a polar molecule. So most molecules are going to be the result of sharing single electrons from two atoms in order to make the overall structure of the molecule. Oxygen has 6 valence electrons, hydrogen has 1, and so the single electrons are the ones you're going to use to make these covalent bonds. And then you should end up with usually 8 overall for the valence shell of a atom, with the exception being hydrogen, which is happy with 2. And then if you are good at that, doing it in your head, you can go right to a stick diagram, which shows the bonds as aligned rather than circling 2 electrons. So there you go. Okay, so let's draw a few. What you want to do is put the atom with the most free electrons in the middle. So this nitrogen has 3, hydrogen we know only has 1, and so conveniently we can show the sharing of each of these in order to end up with a complete outer shell for everything. So nitrogen ends up with 2, 4, 6, 8. That's great. Hydrogen is happy with 2. You can draw a cleaner one if you are at that level. You can go straight to the stick diagram. Carbon here is the one with the most to share. It has 4, where the oxygen only has 2 that are single. And so the oxygen you could draw above here if you like. Try to arrange the free electrons so that they are convenient to each other. You don't have to do weird squiggly circles to get to the free electrons. And you'd end up with something like that. Again, you can double check by counting that each atom ends up with a full outer shell. And then the nice clean version would look something like this, with a few valence electrons there. This last one's more structural. It's to give you clues as to what is attached to what. You see hydrogens in 2 spots. And so the first part is nitrogen with 2 hydrogens attached, and the second part is this carbon with these oxygens attached. You can see even the oxygens aren't listed together, so that means that they're not attached to each other either. So you end up with a nitrogen to the carbon. This nitrogen has 2 hydrogens attached. And then the carbon is to 1 oxygen and then to the other oxygen, and then that goes to the hydrogen. So this must be a double bond. And you can fill in any of the excess valence electrons as needed. Yeah, so again, double check, make sure everything has 8 valence electrons or 2 if it's hydrogen, and you're good. So the only naming we're going to do with molecules is for binary molecules. Binary means 2 elements. And so they're all going to end with IDE, just like the beginner compounds that you would have done in grade 9 or 10. And they use prefixes in order to denote how many of each element is in the molecule. So if there's 2, then you'll use the prefix di, and if there's 4, you'll use the prefix tetra. So this guy here would be dinitrogen tetraoxide. I've seen people drop the A, so it's just tetroxide, but either one, I think it's fine. When there's only one, especially at the beginning, you don't have to use the prefix mono, so not for the first element. So we don't have to say monosulfur trioxide here, it's just sulfur trioxide. Phosphorus pentachlorides, that just means 1 phosphorus, pentas 5, and so Cl5. Dihydrogen monoxide, I wonder what that could be. So dihydrogen is 2 hydrogens, monoxide is 1 oxygen. Hey, surprise, surprise, it's water. So due to variations in the amount of intermolecular strength, you can have all different states of molecular compounds, as opposed to ionic, which are always those crystals. So with molecular compounds, you can have crystals like sugar, but you can also have these solids that are more amorphous, like wax, or gases like butane, or liquids like vegetable oil, right? So there's quite a bit of variation, and that's due to the differing ways in which molecules can stick together. So you get quite a range, generally lower melting and boiling points than ionic compounds. And conductivity is pretty bad with molecular compounds because there isn't any free ions to move around and limited ways for electrons to get from one molecule to another. Okay, almost done here. On this slide, I just want to point out a place where many students get a little mixed up. And that is when they see the same formula in an ionic compound as in a molecule that stands alone. So a couple examples here. Here's SO3, but it's part of an ionic compound with sodium. So this is sulfite. Here's SO3, but it's not bonded to anything. It doesn't have a charge, and so this is sulfur trioxide. And it has to do with the way in which it's bonded. You can see there's these extra electrons with the sulfite that are not present with the sulfur trioxide. And so just keep an eye out. If it's part of a bigger compound, especially with a metal or another positively charged ion, then you're going to use the ionic name for it. And if it's all by itself and doesn't have a charge, use your prefixes. Here's another one here. CO2, I've had students say, well, this is clearly calcium carbon dioxide. But that's not the name for the ionic form of carbon with two oxygens. So with the extra electrons, that's carbonite, not carbon dioxide. This guy here, of course, is carbon dioxide. And you notice no charge. Okay, hope that helps you out. Alrighty, lastly, some molecules that everybody should know. Some hopefully you already figured out, things like carbon dioxide. Most people know that one. You talk about it a lot in biology, right? Because you are exhaling it all the time due to metabolic processes that produce that as a waste. Good old vinegar, that's a good one to know. It's the classic one that has the COH group on it, and we use it for lots of different things throughout high school. Methane, that's the main gas that comes out of the tap when we light up a Bunsen burner. Ammonia, which is similar to methane, just got nitrogen in the middle instead of carbon. Ethyl alcohol or ethanol. This one is one that's around in everyday life. Of course, anything that's alcoholic will have this alcohol in it. The eth refers to the two carbons, and the alcohol part is this OH group that's on there. So that's one that you might not have seen before, but I just wanted to plant the seed because later on we tend to see these more and more. And of course, good old glucose, which is part of things like sugar. Sugar is a disaccharide, which has two of these stuck together in various variations. But you can see the basic structure of glucose has lots and lots of these oxygens, all bonded to a chain of carbon. This is the chain form. There's a ring form as well that you'll learn about later on, but also a famous molecule. And if you're trying to think of examples, it's good to have a few in your back pocket that you can refer to. Okay, hope that helps. We'll see you soon.